Hello, my name is Nicholas Antonio and I'm a student at Curtin University beginning my honours degree in mathematical physics this year. My project for the 2021 to 2022 Pawsey summer internship was the study of electron capture processes in bare beryllium ion collisions with excited hydrogen. More specifically, I model a beryllium nucleus with no orbiting electrons colliding with a hydrogen atom, and then calculating the probability that this beryllium ion will steal the electron from the hydrogen target to form a beryllium 3+ ion in a particular excited energy state. More technically, we express these measures of probability through quantities called total and state-selective electron capture cross-sections. Calculating these electron capture cross-sections is important because major fusion projects such as ITER and JET seek to use beryllium-containing materials in their plasma-facing components. Thus, given the high temperatures that are to be achieved inside such fusion reactors, the beryllium atoms in the wall can erode into the plasma and ionize to become beryllium 4+ ions. To determine the effects that these ions have on the temperature and density of the plasma requires the knowledge of these electron capture cross-sections. However, what makes this a challenge is, to this date, there exists no experimental measurement of these cross-sections for this particular collision system. Therefore, providing this data for fusion diagnostics is left solely to theoretical calculations using supercomputing clusters. To perform these calculations myself, I have used the wave packet convergent close coupling approach, or WPCCC method for short. This method is constructed using the theory of quantum mechanics and ultimately requires solving a large system of coupled first-order differential equations to calculate these desired cross-sections. To obtain accurate results often requires solving on the order of thousands of these fully coupled differential equations, and thus we use the Topaz cluster at Pawsey to perform such calculations. Over the course of the internship, I was able to calculate a large number of total and state-selective electron capture cross-sections for beryllium 4+ hydrogen collisions. As an example, here I show my results for the total electron capture cross-section as a function of projectile energy alongside previously conducted calculations. In summary, here we find our WPCCC results shown by the red points to be in good agreement with recent studies that use methods referred to as the GTDSE and CTMC methods. However, interestingly, we also find significant disagreements to data obtained using an AOCC approach across a large collision energy range. In conclusion, being able to provide accurate data that is required for plasma diagnostics research is a small but necessary piece of a grander goal, which is to be able to provide clean and sustainable energy to the world via fusion reactors. Also, continuing this research into the future, I aim to calculate these cross-sections at a greater number of collision energies and study other atomic collision systems that will also be relevant for plasma impurity diagnostics. Over the course of the Pawsey internship, I have learned many important skills relating not only to high-performance computing, but also in science communications through the workshops taught by the amazing staff at Pawsey. Both areas which I believe to be of great importance for my future career path. I strongly recommend to those who are passionate about science and computing in applying for the next Pawsey summer internship program. Thank you very much for listening.